Hello, I'm Mihail Soroyu, and I'm the PHY architect at DAC Semiconductor, which is a subsidiary of OPENEDGES technology. And what I will cover today is the memory subsystem design challenges and the need for flexibility. As a table of contents, what I'll cover is the main challenges, the DDR training complexity, and the need for flexibility. And we're going to investigate a couple of solutions that exist in the solution space, and basically how the OPENEDGES PHY differentiates itself from other customers and other vendors. So what are the today's challenges? Mainly is the fact that in LP5 and DDR5, the peak data rates were pushed past the 5 gigabits per second mark, while at the same time, the physical challenges remain mainly the same. On top of that, the DRAM protocols are evolving fast. There are a lot of DRAM protocols. And on top of that, there are more and more DRAM vendors on the market. And all that we have to cover for our customers. I like this statement. Gone are the days of just meeting, set up, and hold on the DRAM interface. Whoever remembers back in the day when we would just estimate the output and input delays and we would just close timing once, those are gone. Interfaces today require training to center the data sampling points, and we need to do that dynamically. As an example, in LPDDR5, we have many levels of training, starting with a command bus training, which implies aligning the command bus to the CK, write leveling, which aligns the write clock to the CK, read gate training, which identifying the valid window for the read burst. Of course, centering the I for read and write. And on top of this complexity, we have to do this periodically, sometimes to minimize the traffic stop or not stopping traffic at all. Why do we need this flexibility? Simply because the training algorithm has to change based on platform, based on protocol, and has to be adjusted to any DRAM vendor. We need to change training patterns, training steps have to be reordered, and of course everything has to be done as fast as possible. The operations are not as simple as they used to be. They're no longer just simple offsets or logic operations. We have to perform more complex averaging, weighted calculations, division, multiplications, and so on. And all this stuff has to be done real time. And on top of all this, we have to trigger this asynchronously to the actual DRAM operation, and it has to be done as like interrupts. So all these are very complex operations. So let's look a bit about like what's possible to be done in the solution space. So I'm trying to list like the extremes of the solutions, the hardware and the software, just to emphasize how like the OPENEDGES solution would be the best of both worlds. On the left side, we have the hardware, which obviously means everything is done in hardware, is as fast as possible. And on the other side, the software solution, where practically implies the minimum amount of hardware that can be controlled by software and can still perform the function. I won't talk yet about the firmware because I want to introduce first the cons of the two extremes. Obviously, the hardware means to be able to cover all the possible protocols and variations. It implies a large area overhead. While on the software, of course, because it's software, we can control a lot of protocols. On the other hand, everything is software, so it implies platform software dependencies and usually is very slow. So OPENEDGES focuses on the middle solution, where is as in the firmware. This means we have the minimum amount of hardware and we embed the software inside via our proprietary microcontroller. So we think this is the best of both worlds because it provides both the minimal area but maximizes the flexibility. So this is how we introduced the PSM, which stands for Programmable State Machine. It's really a lot to say it's a microcontroller. I like to see it more as a programmable state machine, simply because it's a bit more than a finite state machine. We have just a bit more programmability of the states. We can swap them. We can attach some logic operations to the states. But we like to also call it as a microcontroller. Because it operates in a similar manner. It possesses 64-bit instructions. Of course, we have external event synchronization, so we can breakpoint, we can fully debug during the bring up. We have custom interface to drive the training hardware, which operates as an external accelerator. This is how we can achieve minimal training time compared to our competitors. We have a miniature ALU for performing all these arithmetic operations. And of course, we have a dedicated CA interface, and that's a unique part of our PSM. It can sequence any DRAM command in a real-time manner. On top of that, we also have a micro version of the PSM, which we call a micro PSM, which is really a small core microcontroller. It's a stripped-down version of the main PSM, which only has 32-bit instructions, which much less instruction than the PSM. And we have removed the CA interface and minimized the ALU. It's really just logic operations. So this is really how the micro PSM looks like. How do we use this? Well, it's pretty simple. We identify on the application what are the functions that the PHY has to execute at the same time, like in parallel. Based on that, we simply assign functions like threads, right, to our PSMs. For example, we achieve parallelism for concurrent operations to minimize the PHY initialization. For example, the thread 1, which is the main PSM, can do periodic training or like initialize the training, while the other micro PSMs, one can do periodic calibration of all the internal PHY engines, while the other one can be triggered and can dynamically monitor the DFI interface. So practically with this, we can address any variation of the DRAM standard and customize the solution for our customers. So really, to adapt to the complexity of today and future DDR interfaces, we really build the necessary brain power. So this is what I like to say, we're doing what's right and not what's easy. This is really like, I like to see it as a multi-threaded firmware that we have to do, which is fairly complex. But of course, the road does not end here. We'll continue to refine and fine-tune our PSM to differentiate ourselves even further. Thank you.